Okay, the next concept in the design of compression member is built-up column. So first, before going into the discussion of this, first of all, what is meant by built-up column? Come on, think, what is meant by built-up column? So built-up column is nothing but increase in cross-section is known as built-up section. So whenever we are going to increase a cross-sectional area, then such a type of connection is known as built-up. Okay, so now here we are going to increase the cross-sectional area of a column. That is why it is called as built-up column. So when we are going to increase a cross-sectional area, for example, we know that we are discussing in the introduction itself, all the structural steel members are manufactured. Okay, so before using them, they are already manufactured. So whatever the structural steel members are there in the market, so those we are going to order and we are going to use in our steel structures. Agree or not? It means area of that structural steel is fixed. Okay, area of that structural steel members is fixed. So now the question here is based on the design procedure. If you see if you go through the design procedure, there we are going to calculate the required area based on the factor design load and then design stress. Agree or not? Based on that, we are going to calculate the required area. So after deciding or calculating the required area, we are going through the steel table. So in the steel table, the every detailing of the structural steel members which are manufactured in the various industries and steel plants are mentioned. So there exists a case such that throughout the steel book, okay, in the total entire steel book, there exists a no cross section to match with the required area. Then what is the situation? That is the question. So if you go through the entire steel table, okay, entire steel table, that IS handbook number 1 or entire steel table book. So in that steel table book, there exists no cross section to match with the required area. Then what is the situation? So that is the question. So in that case, we have to go for this built-up section or built-up column. It means we have to increase the area. It means by connecting or joining two members or more than two members or more than one member, we are going to increase the area. So that is known as built-up column. So obviously, when is the requirement of built-up column or when we go for built-up column? If area, okay, if the area of the selected trial section from the steel table is not matching with the area required, then we should go for it. Okay, so that is the condition. So if required area is more than the rolled steel member, then we go for built-up section or built-up column. Then we go for built-up column. So this is one of the condition. Okay, this is the one of the condition for going the built-up column. As it is the column. So in the column, which factor plays a major role? Slenderness ratio. Agree or not? So slenderness ratio plays a major role. For example, in that slenderness ratio, if you see the formula of slenderness ratio, what is the formula of slenderness ratio? Effective length by minimum radius of gyration. If the minimum radius of gyration is minimum, okay, if the minimum radius of gyration is very much less, then slenderness ratio will be more. Agree or not? If slenderness ratio is more, then more chances are there for that column to buckle. Okay, then more chances are there for that column to buckle. So for that, to reduce the slenderness ratio, we have to increase the minimum radius of gyration value. Agree or not? So we have to increase the minimum radius of gyration value. So that is also the condition for going for the built-up column. So second condition is to increase the minimum radius of gyration. Okay, to increase the minimum radius of gyration. So these are the conditions for built-up column. So this is the, if such situations are prevailing, then we go for or then we prefer built-up columns. Okay, when we prefer built-up columns, what are the conditions? So tell me. One is if required area is not matching with the area, gross area of standard rolled steel section, and then if radius of gyration is minimum, okay, if minimum radius of gyration is minimum or less, then these are the conditions for going or for preferring built up column. Agree or not? So these are the conditions for preferring the built up column. Clear? So how to increase this minimum radius of gyration? By going for built up column. So upon providing the built up column, how to increase? Just with an example I am going to explain. So see the diagram. So this is a channel. Okay, this is a channel. Okay, this is a channel. So about this channel, each and every detail of this channel is mentioned in the steel table, like. So this is the x-x axis of this channel, okay, and this is the y-y axis of the channel, and here where the CG lies. Agree? And this is the width. And this is the thickness of the web, TW. Okay, and this is the thickness of the flange, TF, and this is the overall depth, D. So like that, every details, and that too here x and y are major and minor axis. Yes or no? So we know when the axes are called as major and minor axis. If the product of inertia about those axes is 0, then those axes are called as major and minor axis. So IXX, okay, IYY, and then RXX and RYY are given. So out of these two, which is minimum radius of gyration? You tell me. So we know that XX is major axis, then obviously IXX is much greater than IYY. From this you can say RXX is much greater than RYY. So you can say that here RYY is the R minimum. Agree or not? Agree or not? So this we discussed in the introduction itself. So here RYY means radius of gyration of this channel about YY axis is the minimum radius of gyration. So this is the minimum radius of gyration. So now this is called as radius of gyration for a component. So actually minimum radius of gyration. Okay, add this. Minimum radius of gyration for a component. So now I am going to connect these two cross sections, and that too the area of this channel is AG cross area. Okay, area. So these are the detailing of this channel. So now I am going to connect this channel with other channel. So how it is? See here. So this is the channel. This is one channel, and I am going to place another channel like this. These are the two channels. So now I am going to connect these two channels. Agree? I am going to connect these two channels by using some members like this. Now see here, after making, it looks like a box section or not. So previously there, this is the channel, C shape, but after making a connection, they looks like a box section. Now all the things will change here, like area will change, and then moment of inertia about major and minor axis will change. So everything will change. Agree or not? So if you see here, for this section, box section, this is known as built up section. So for this section, this is considered as a XX. Okay, and this is considered as a YY. And here where the CG lies. Agree or not? Here where the CG lies. And obviously we know that area. So area of this built up section is twice that AG. So area of whole column. So this is whole column or built up section. Built up column or whole column. WC is nothing but whole column or built up column. So is equal to twice the area of individual channel. Agree or not? And Ixx, what is Ixx in this case? We know that this is the XX for the individual column. Sorry, YY. And this is the YY for this column. But XX is same for individual component or individual channel or component and whole column. So now in this case, Ixx of whole column, means this built up column, is twice the Ixx of that component. Agree or not? Now, how to calculate Iyy? That is the question. How to calculate Iyy here? So see here, Iyy of whole column. See, WC is nothing but, here I am writing, WC is nothing but whole column. How to find it? So this is the Iyy for component. Agree or not? Now we want the moment of inertia about this. So now for this we require this distance. Yes or no? So for this we require this distance. So how to calculate this distance? Tell me how to calculate this distance. See here. This is the spacing. So just 1 second. So here where the CG lies, CG of the whole column lies. So we can say that this is total is known as spacing. Agree or not? Spacing between these two columns, or you can say spacing between these two channels or components of a column. So how much? Assume it as a x. Assume it as a x. Now to calculate the moment of inertia of the whole column about this YY, we require this distance. Agree or not? We require this distance. How to calculate this distance? So if you observe, this distance consists of here where the CG of the component lies, here where the CG of the component lies, here where the CG of whole column lies. So now the CG of this column is also mentioned in the steel table. It means we know this CG. It means this distance we know it. That is mentioned in the steel table. Okay, this distance CG is mentioned in the steel table. That is known as CGXX. It means centroid in XX direction. So now from the width of the flange BF, width of the flange BF minus CGXX, we are going to get this value of. So total is C. Observe here, total is BF, width of the flange. Total is width of the flange. So from this width of the flange, if we deduct this value, we are going to get this value or not? So after getting this value, if we add x by 2, we are going to get this value or not? Then we are going to get the total distance. Clear? After getting the total distance and by using parallel axis theorem, can we find the moment of inertia about YY or not for a whole column? So how to find it now? Twice Iyy plus Ag. So give some notation here. It is in x direction, already we have used. So give it as S. Agree. So what is the value of S here? S is equal to BF minus CGXX, means width of the flange minus center of gravity of the channel component of the whole column in x direction, plus spacing between half of the spacing between those two columns, that is S. So Ag plus S square. Ag into S square. So this is a parallel axis theorem. This is a parallel axis theorem. So in this way we can calculate the moment of inertia of the whole column about YY. Agree or not? Moment of inertia of whole column about YY. So if you want, write down the terms here. X is spacing between the column or spacing between the channels. So rest everything is known to us. Is it clear? So take this diagram clearly. So this is one channel, this is one channel. So we have connected those channels by using one member that is known as flat, and here these are boards. So after connecting, this looks like a box. So this box will have two axes, that is XX and YY, and here where the CG of the box lies. So to find out the moment of inertia of this built up column or whole column or this box cross section about x and YY. So XX is simple. It is simply twice the Ixx of the individual component. Agree. Now coming to the Iyy, we have to apply parallel axis theorem. For that, we should know the distance between the component y axis and whole column y axis. So this is S. So to calculate S, we should know the CG in X direction that is given in the steel table, and then the spacing. So as we are designing this, as we are making this built-up column, so we prefix this spacing. So X is also known as the spacing between those two channels. So based on that, width of the flange of the channel is also given in the steel table. So based on that, we can calculate S. After getting that, we are going to calculate I by y of whole column. So now this I by y of whole column depend upon the spacing or not? X. Agree or not? So if we provide more spacing, then more value for I by y we are going to get or not? So if you see for an individual component, then Ixx is more than I by y, no doubt. Then obviously Rxx is greater than R by y, so R by y is the minimum. So if the radius of gyration is minimum, then slenderness ratio will be maximum. So now more chances are there for that component to buckle, or that for that column to buckle. Agree or not? So now we are by providing a spacing, we are increase the minimum moment of inertia of whole column or not? Agree or not? So we are going to provide this spacing X such that Ixx of whole column is approximately equal to I by y of whole column. Then in this way we are going to increase the minimum radius of gyration or not? So we know that what is the so define radius of gyration in terms of moment of inertia. So moment of inertia I is equal to area into radius of gyration. Agree or not? So if we increase area, then R will also increase. If we increase moment of inertia, then R will also increase. So by providing some spacing and by providing built-up column, we are increasing the minimum moment of inertia. Agree or not? So we are making it as equal to maximum moment of inertia, so that radius of gyration will also increase. So as radius of gyration increases, then slenderness ratio decreases, so that buckling chances are less. Agree or not? That is the thing. So these are the two criteria for going the built-up column. So this is the condition. So this is how we are going to increase the minimum minimum radius of gyration, and of course we are increasing minimum moment of inertia, so that minimum radius of gyration is also increasing. Upon increasing the minimum moment of inertia, minimum radius of gyration is also increasing. So this is the way. I guess this is a simple strength of materials concept and engineering mechanics concept, but still this is required here. So in this way we are going to increase it. So now that increase in minimum moment of inertia all depend upon the spacing. Okay, so here the spacing plays a major role in built-up column. So based on that only, that R minimum radius of gyration is going to increase. Take it down. So take that diagram clear. Okay, so this is about the condition for going for built-up column. Next, now how we are going to provide this built-up column? It means system of built-up column. So we can provide a built-up column by using two systems, or by using two patterns. Okay, by using two patterns we can provide built-up column, or by using two systems we can provide built-up column. Those are either by lacing or by battening. So we are going to provide these built-up columns, or we are going to make this built-up column either by using lacing or by using battening. Either by using lacing or by using battening. So these two are the systems of making this built-up column. So generally we prefer lacing if column is eccentrically loaded. If column is eccentrically loaded. So what is meant by eccentrically loaded? Along with the concentric load, there acts a moment. So that is what eccentrically loaded. So if column is eccentrically loaded, then we make the built-up column by using this lacing. Okay, by using this lacing, we made a built-up column if that column is eccentrically loaded. The load on that column is eccentric. So if column is axially loaded, then we go for battening. So then we make that built-up column by using battening. So these two are the system of built up columns. Clear? So now Kubernetes lacing. So first we discuss lacing and all the detailed provisions regarding this lacing given by the IS code, IS 800, and then we go for backend. Okay. So take it down. So I am Kubernetes lacing or lacing system.